We come to the third exercise of circles. In this, the very important theorem comes: angle subtended by an arc of the circle. Angle subtended by an arc at the center of a circle is double the angle on the remaining part of the circle, right? So this is the next and the last exercise, 9.3. So if you look at this diagram here, PQ is an arc and this is the angle made by PQ at the center. And this is the theorem, very, very important theorem. Angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. This theorem is very, very important, right? So here there are considering three cases. PQ is the arc. PQ is the arc. And this is the angle being subtended at the center of the circle. This is the angle on the remaining part. So here we have to prove that angle POQ, that is the angle at the center, is double the angle on the remaining part. Angle at the center is double the angle on the remaining part. So the angle at the center is angle POQ, and angle on the remaining part will be angle PAQ. So here there are three figures given. The proof is same. So I'm just going to explain that to you first. So POQ angle at the center is twice of the angle subtended by the same arc on the remaining part. So P and Q is the starting and ending point. This is the angle being made at the center of the circle. And this is the angle being made by the same RPQ, PAQ on the remaining part of the circle. So why are there three diagrams? Because here PQ is the minor arc. Here PQ is the minor arc. If you see here, the PQ is a semicircle. In the second, PQ is a semicircle. And here, if you see, PQ is a major arc. So that is why there are three diagrams. Now I'm going to number these to make it easier. So I'm numbering this 1, 2, 3, 4, 5, and 6. Same numbering I am going to follow in all so that the proof will be identical for all. So 1, 2, 3. Okay, and this angle here 4, this angle 5, and this angle 6. So I'm going to explain to you how to prove that angle POQ is twice of angle PAQ. So numbering is very important. I've numbered it all three diagrams in the same pattern, and the diagram is different. As I told you, here PQ is minor, here PQ is a semicircle, and here PQ is a major arc, and it is valid for all the three cases. So if you look at this triangle now, triangle OPA, angle 1 becomes the exterior angle. And we know that exterior angle is sum of two interior opposite angles. So right now, I'm going to write the proof. I will say angle 1 is equal to 2 plus 3, exterior angle theorem. What is the exterior angle theorems? Exterior angle is sum of two interior opposite angles. So 1 will be 2 plus 3. Same way I can say on this side, this is the exterior angle. These are the interior opposite angles. 4 will be 5 plus 6. 4 will be 5 plus 6. Now, if you look at OP and OA, OP and OA are radius. OP and OA are radius. And if OA and OP are equal, if OP and OA are equal, then the angles opposite to them will be equal. So angle 2 will be equal to angle 3. Angles opposite equal sides. So 2 will be equal to 3. Therefore, I can say 1 will be 2 plus 2. So angle 1 will be twice of angle 2. Angle 1 will be twice of 2. I can repeat the procedure here. I can say that here OA is equal to OQ, radius. Look at OA and OQ, they are radius. And if OA and OQ are equal, then what can we say? Angle 5 equal to angle 6. By the same reason, angles opposite equal sides. If OA and OQ are equal, 5 equal to 6. Therefore, what can we say? 4 is equal to 5 plus 6. 4 is equal to 5 plus 5. Angle 4 is twice of 5. I'm going to add 1 and 2. When I add 1 and 2, what am I going to get? 1 plus 4 is twice of 2 plus twice of 5. And here 1 plus 4. 1 plus 4 is equal to twice of 2 plus twice of 5. So I'm going to take 2 common, I'll get 2 plus 5. What is angle 1 plus 4? I'm going to get angle POQ. And twice of what is 2 plus 5? 2 plus 5 will be PAQ. So I am proving for one, and then I can say similarly, angle POQ can be proved equal to twice of PAQ in case 2 as well as case 3. So I'm proving this entire thing for one. I have kept the numbering same, so I don't have to repeat the whole procedure 3 times. I can say similarly, if 1 plus 4 is twice of 2 plus 5, angle POQ is twice of PAQ. This is valid for all the 3 diagrams. So this is a very important theorem, degree measure theorem, or angle subtended by an arc at the center is double or twice the angle subtended by the same arc on the remaining part of the circle. Next theorem, angles in the same segment are equal. Angles made by the same arc. If you look at PQ, PQ is an arc. Starting is P, ending is Q. Angles subtended by the same arc are equal. So angle PAQ is equal to angle PCQ. Angle made by the same arc or angles subtended by the same arc are equal. So whenever we are having an arc AB, any two angles subtended by them or more than two also, angles subtended by the same arc are equal. So if you look at this angle ACB equal to angle ADB, remember your starting point and ending point has to be same and it has to lie on the circle. These points also are on the circle. So ACB equal to ADB. If this is 40, this will also be 40. So this is our theorem. Angles in the same segment are equal. Next, we come to the concept of cyclic quadrilaterals. Now, what is a cyclic quadrilateral? A cyclic quadrilateral is a four-sided figure. Look at this. 4 points on the circle. These are 4 points on the circle, A, B, C, D. If opposite angles add up to 180, this is cyclic. So A plus C is 180. B plus D is also 180. See, this is 4 points. These are 4 points. When I join the 4 points, I get cyclic quadrilateral. Opposite angles of cyclic quadrilateral will add up to 180 degrees. Now let's go to the exercise. The first question is a simple question. Here we have two angles 60 and 30. The question is find out angle ADC. So just now we did the theorem, angle at the center is double the angle on the remaining part. So here if you see angle AOC is made up of two small angles 60 and 30. So when I add that, I'm going to get 90. So angle at the center, AOC, is twice the angle on the remaining part. This is the theorem. Angle at the center is always double the angle on the remaining part. It is C starting from A, ending as C. AOC, this is the angle at the center. And this is the angle on the remaining part made by the same arc AC. So AOC was given 90. So ADC will be, this angle will be half of 90. So this angle will be 45 degrees. Always the central angle is double the angle on the remaining part. So this is 90, this is half of 90, this will be 45. Question number 2. A chord is equal to the radius. Now let's see question number 2. A chord is equal to the radius. This is AB. This is the radius. It is given that the length of this chord is equal to the radius. That means AB and OA and OB all are equal to R. Therefore, this is an equilateral triangle. Find the angle subtended So the chord is equal to the radius means AB, OA and OB are equal to R. Find the angle subtended by the chord on the minor arc. Now here the minor arc is minor arc is this AB. So let's say this is the angle being subtended by AB on the minor arc. And we also have to find the angle on the major arc. Let's assume that this is a point on the major arc. So we have to find out this angle as well. So there are two angles we need to find here. One is angle ACB. This is the angle in the minor arc, and this is angle ADB. This is the angle in the major arc. So first, this is all equal. So this becomes an equilateral triangle. So we know that if it's an equilateral angle, this will be 60. So straight away, we have got this angle AOB as 60 because triangle AOB is an equilateral triangle. So this is 60. Now we just did the theorem that angle at the center is double the angle of the remaining part. So if this is 60, this is going to be half of 60. Angle ADB will be half of 60. So this angle will be 30 degrees. Angle at the center is double the angle of the remaining part, 60, 30. Now, if you look at this ACBD, it's a cyclic quadrilateral. And just now we did this theorem that if there is a cyclic quadrilateral, opposite angles will add up to 180. So angle D and C together will add up to 180 because it's cyclic. All the 4 points are on the circle. And D value we have found out 30. So C will be 180 minus 30. So this angle C will be 150. So angle made by AB on the minor arc, and that is angle C here, ACB, this will be 150. And angle on the major arc, that is angle ADB, will be 30. So your answers will be ADB 30 and angle ACB 150. Then we come to question 3. Question number 3, figure is given here. This angle is given 100 degrees. Find out angle OPR. You have to find out this angle OPR. So again, this is 100. Angle at the center will be double the angle on the remaining part. So this will be 200 degrees. This major angle POR will be 200. So the inside angle here is going to be 360 minus 200. Because we know it's a complete angle. Total is 360. So angle POR, that is the minor one, is equal to 160 degrees. So this inside angle will be 160. Now OP and OR are equal because they are radius. OP and OR are, OP is a radius, OR is also radius. OP and OR are radius. Therefore, they are equal. So if they are equal, angles opposite to them will also be equal. So we can assume angle OPR and ORP to be X. Now, if you look at the triangle POR, this is a triangle. Sum of angles is 180. So 160 plus X is 180. Sum of angles is 180. So this is 160. We have assumed these two X because both these angles are equal. 2X is 180 minus 160. 2X is 20. So X will be 20 upon 2. So we get the value of X as 10. So our answer, angle OPR, this angle will be 10 degrees. Angle OPR will be 10. Clear? Now we go to question number 4. That is 9.25 figure. Angle ABC is 69 degrees. This total is 69. This angle ACB, this total is 31. Question is find BDC. Very easy question here. Now we know that this is 69 and 31. ACB is 31, not full angle. ACB. It's only here. So what I need to do is take triangle ABC. We know that sum of angles of this triangle ABC is 180. So 69 plus 31. This is 69, this is 31 plus angle A is 180. Sum of angles of a triangle we know is 180. So we are taking triangle ABC. 69 and 31 will give us 100. So angle A will be 180 minus 100. So angle A will be 80 degrees. So this will be 80. Now we have done this theorem that angles in the same segment are equal. So angle BAC and BDC, see, starting from B ending with C, BAC, BDC, and these 2 points are on the circle. These is angles in the same segment. So both of them will be 80. So this is 80, this will also be 80. Angles in the same segment are equal. So answer BDC 80 degrees. Then question number 5. These are 4 points A, B, C, D on the circle AC and BD intersect at the point E. Now here this is given 130 and this is given 20. Find angle BAC. We have to find out angle BAC. So what we can do is find out angle CED first. See, this angle is given 130. So this is linear pair. I can find out this 180 minus 130. This is going to be 50 degrees. Now we know the two angles of this triangle EDC. We can easily find out the third angle by angle sum property. This is 50 and 20. So I can find out angle D. So 50 and 20, 70. You will get 180 minus 70. So angle D will be 110 degrees. So this angle is 110. Now the question is find out BAC. Now using the same theorem, angles in the same segment. Look at B and C. This is an arc BC. BAC and BDC will be equal. BAC and BDC will be equal. Now BDC we have already got 110. Right? 650 and 20 was 70. 180 minus 70, 110. So if this is 110, angle BAC will also be 110. Angle BAC equal to BDC. Remember, your starting and ending point has to be same. Angles in the same segment are equal. So that's question number 5. Then we go to question number 6. When we come to question number 6, ABCD is a cyclic quadrilateral. So here I am taking a circle, taking a quadrilateral. Cyclic means all the 4 points are on the circle. And here the diagonals are intersecting at a point D. Diagram is not given, we are making this. Angle DBC is given 70 degrees. This angle DBC is 70. Angle BAC is 30. This is 70, this is 30. Question is find out angle BCD. This angle we have to find out. And second part, if AB and BC are equal, find out angle ECD. So we have made the diagram. Already 2 angles are given. With this first thing is to find out angle BCD. This angle has to be found. Now to prove that, see here, see this BC is an arc. So angle BAC. This is the angle BAC starting from B ending with C. BAC will be equal to BDC. Angles in the same segment are equal. So BAC is 30. So BDC will also be 30. Look at BAC. BDC. These 2 angles are going to be equal. Now we can find out angle BCD because sum of angles of a triangle is 180. So you take triangle BCD. Already we know 2 angles, 30 and 70. So we can easily find out the third angle BCD. 70 and 30 is 100. So 100 plus BCD is 180. So angle BCD will be 180 minus 100. So angle BCD will be 80 degrees. So this is the first part. Second part, AB and BC are equal. So these 2 are equal. AB and BC are equal. Now in triangle ABC, whenever we know that in a triangle 2 sides are equal, the angles opposite to them will also be equal. So if AB and BC are equal, angle BAC will be equal to angle BCA. and this angle is 30, so this angle will also be 30. Angles opposite equal sides. Now the question is find out angle ECD, that means the remaining angle. This total angle was 80, this angle we have found out 30. So what will be angle ECD? That will be simply the total angle 80 minus the angle that we took out just now. This angle that we have taken out now is 30 degrees. This angle BCA is 30. So 80 minus 30. So this answer will be 50 degrees. Angle ECD will be 50 degrees. Moving on to question number 7. If the diagonals or diameters, if the diagonals are diameters, prove that it is a rectangle. So you are having a figure in which the diagonals are actually diameters. Prove that it is a rectangle. So this is the diameter, means it will pass to the center. To prove that it is a rectangle, we need to prove that all angles are 90. So since AC is diameter, this is AC is diameter. So this is semicircle. You know the diameter divides the circle into two equal parts. This is the semicircle. And therefore we can say that angle ADC is 90. Angle in a semicircle is 90. Same way angle ABC is 90. Angle in a semicircle. Remember this theorem. Whenever we are having a diameter, it divides the circle into two parts, and the diameter divides this into two parts, and the angle in any angle that you make here is going to be 90 degrees. The starting is A, ending as C. AC is the diameter, right? So this is 9. If I look at BD, BD is also a diameter. So if BD is the diameter, this is a semicircle, then this angle will be 90. Again, BCD and angle BAD, both angle BCD and angle BAD will be 90. This is 90, this is diameter, this is also 90. Now all angles are 90. And if all angles are 90, that figure ABCD becomes a rectangle. Right? Then we go to question number 8. If the non-parallel sides of a trapezium are equal, important question. If the non-parallel sides of a trapezium are equal, prove that it is cyclic. To prove it is cyclic, we have to prove that opposite angles add up to 180. So the non-parallel, these are the parallel sides of a trapezium. Non-parallel sides mean the AD and BC. It is given that the non-parallel sides are equal. So AD and BC are equal. And of course, the other side, AB and CD are the parallel lines. We have to prove that it is cyclic. So to prove this, there is a construction. And what is the construction? Draw CE parallel to AD. Draw CE parallel to AD. Now we are drawing this line parallel to this. Now we are going to number this 1, 2, 3, and 4. And if I want to prove that this figure is cyclic, I have to prove that 1 plus 4 is 180. Now, by drawing CE parallel to AD, actually what have we done? We've got ADCE is a parallelogram. ADCE is a parallelogram. Now, why is that a parallelogram? Because already CD and AB are parallel. CD is parallel to AB. That means CD will be parallel to AE as well. And AD is parallel to CE. AD and CE are parallel. Why is AD and CE parallel? By construction. This is given and this is by construction. So that is why we say this is a parallelogram. And we know that if it's a parallelogram, opposite angles are equal. Opposite angles are equal in a parallelogram. So we can say 1 and 2 are equal. So this part understood. Now we go to the next part. See, AD is equal to CE. Opposite sides of parallelogram are equal. AD and CE are equal, and AD is equal to BC, already given. Two things equal to the same thing are equal to each other, therefore BC equal to CE. We can say BC equal to CE. See here, AD is equal to CE. Opposite sides of parallelogram, AD equal to BC given. AD is common, therefore BC and CE are equal. Therefore, we can say if the sides are equal, angles opposite to them will also be equal. So here we've got angle 1 equal to 2, here we've got 3 equal to 4. Now 2 and 3 form a linear pair, so 2 plus 3 is 180. Linear pair. Now instead of 2, I can replace it with 1 because we have already proved that 2 and 1 are equal. And instead of 3, I can write 4 because I have proved that 3 equal to 4. So what will I get? 1 plus 4 is 180. This is from 1 and 2. So angle 1 plus 4 is 180. Opposite angles are adding up to 180. Therefore, what can I say? ABCD is a cyclic quadrilateral, or ABCD is cyclic. So very important question. If non-parallel sides of a trapezium are equal, prove that it is cyclic. Question number 9. Question number 9. Two circles. The diagram is already given. We have to prove that angle ACP is equal to angle QCD. I have numbered these 1 and 2. Let these angles here be 3 and 4. So diagram is a little complicated, but the proof is very simple. If you look at this circle, AP is an arc, so angle 1 will be equal to angle 3. Angles in the same segment. Look at this, ACP equal to ABP. You're starting at A, ending at P. ACP, ABP, angle 1 and 3 are equal. If you look at this circle, DQ is an arc, angle DCQ equal to DBQ, right? Starting at D, ending at Q. DCQ, DBQ. So angle 2 equal to angle 4. Angles in same segment are equal. So 1 and 3 are equal, 2 and 4 are equal. Now 3 and 4 are equal because they are which type of angles? 3 and 4 are vertically opposite angles. Therefore, if 3 and 4 are equal, then obviously I can say angle 1 equal to 2 or ACP equal to QCD. Right? So this is question number 9. Now we come to question number 10. Question number 10. Yes. If circles are drawn taking two sides of triangles as diameter, prove that the point of intersection lies on the third side. So here we are having a circle. Here we have another circle. This is the triangle ABC, and they are saying that the circles are drawn with the sides as diameters. So this is actually passing to the center of this circle. This is passing to the center of this circle. This is diameter. And the question is, prove that the point of intersection of these circles lies on the third side. That means this point, I have to prove that D lies on BC. To prove D lies on this third side BC. This point lies on this. Now to prove that any line lies on one line, I need to prove that it is collinear points. What are collinear points? Lines which lie on the same line. The angle will always be 180. If they are not collinear points, it will not be 180. It will be more than 180 or less than 180. If it is 180, if the points when I join it is 180, indicate that there is a collinear points or it is straight line. So if I am able to prove that this angle is 180, then I can say this point D lies on BC. For that, I will join AD, construction, join AD. Now, these are the two angles. Angle 1 will be 90. Why? Because it is given that AB is the diameter. Angle in a semicircle is 90. And here angle 2 will also be 90 by the same reason, because this is also diameter. Angle in a semicircle is 90. Now 1 and 2 are 90. So when I add 1 and 2, I am going to get 180. And what is 1 plus 2? It is BTC. So once I prove BTC is 180, therefore I can say D lies on BC. Because 3 points, when I join, it will only be a straight line if that angle is 180 degrees. Then we come to question number 11. That is, ABC and ADC are two right triangles with the common hypotenuse AC. So this is AC hypotenuse. Here we have a right triangle ABC, and here we have another right triangle ADC. This is 90, 90. Prove that angle CAD equal to CBD. You have to prove that angle CAD equal to CBD. Now, how is this chapter related to circles? The reason is that this is 90. If it is 90, we know that if this is the hypotenuse, if I draw a circle around this, this will be the diameter, because only angles in semicircles can be 90. So here what we need to do is draw a circle with AC as the diameter. Okay, draw a circle with AC as the diameter. Construction with AC as diameter, draw circle. Now, when we draw a circle here, this is the diameter, so angle in a semicircle is 90. Now, the proof is very simple now. Once we draw the circle, we know that angles in the same segment are equal. So, if you take CD as the arc, angle made by CD, angle CAD will be equal to angle CBD. Angles in the same segment are equal. So, it becomes a one-line proof. If I draw the circle, CD is the arc, angle CAD will be equal to CBD. Angles in the same segment. The last question there, question number 12, prove that a cyclic parallelogram is a rectangle. What is the meaning of a cyclic parallelogram? Cyclic means opposite angles add up to 180, and parallelogram means opposite angles are equal, and then I have to prove it's a rectangle. That means all angles are 90. So this is a cyclic parallelogram. So if it is cyclic, I know that A plus C is 180, because opposite angles of a cyclic quadrilateral add up to 180. And if it's a parallelogram, I know that opposite angles are equal. So opposite angles of a parallelogram are equal. So A plus C is 180 and A and C are equal. Therefore, I can say that both of them will be equal. I can repeat this procedure on the other side. I can same way say B plus D is 180 because it's cyclic. B equal to D because opposite angles are equal in a parallelogram. So this is cyclic. That's why it's 180. It's parallelogram, so it is equal. So therefore, both the angles are 90. Now we have got all the four angles A, B, C, and D 90. If all angles are 90, that figure ABCD becomes a rectangle. So this is the chapter circles. Thank you.